In today's video at Medical Sciences, we're going to discuss about enzyme inhibition, whereby we're going to first look at enzyme kinetics by Michaelis Menten formula. Then we shall look at the different types of inhibition of enzymes. And we begin, we remind you to subscribe. If you haven't subscribed, like the video and share comments so that we can continue to learn together. So in this session, we want to look at enzyme. And if you haven't watched videos on enzymes, please you can go back and check them. It has a playlist known as enzymology so that you can see the introductory part. So enzyme kinetics, here we are going to measure, we are measuring the strength or the affinity of the enzyme. So what it helps us to determine the affinity of enzyme to the substrate and also to determine the substrate which can give good results when we are determining enzymes or when we are preparing reagents and solutions in the lab, so that we know how much amount of the enzyme of the substrate is required to give maximum effect during enzyme catalysis, and also to determine the affinity of the enzyme. That is what is the significance of Km. And according to enzyme kinetics, we are going to see that in presence of the enzyme, if you have the enzyme plus the substrate, you are able to form what we call enzyme substrate complex. And this one is K1, that is a constant reaction K1. And when you want to reverse, it is K2, we are going to refer it as K2. And even after forming the enzyme substrate complex, it has to undergo, we have to release the enzyme, and we form the product. This one becomes reaction free. So these are the ones which we see in enzyme activity or enzyme kinetics, whereby K1, K2, and K3 are constants. And these reactions depend on substrate concentration and environmental conditions like pH and temperature. So these are the ones where they depend on. And using these kinetics, we can develop Michaelis Menten equation, whereby Michaelis Menten equation is equal to Vmax times enzyme substrate times substrate concentration, whereby here we have V naught. V naught is equal to Vmax, enzyme substrate concentration, divided by the Km, which is Michaelis Menten constant, plus substrate concentration. So this is what we call Michaelis Menten equation, and this equation helps us to determine the significance or the purpose of this is to help us to determine the maximum substrate concentration required during enzyme catalysis, and also to help us to determine the affinity of the enzyme. So this is what is the significance of this Michaelis Menten equation. And after looking at this, you can ask yourself, how can we determine Vmax and how can we determine Km and V naught? So this one I can illustrate it on this graph, whereby here we have substrate concentration. Then here we have V naught, enzyme velocity. Then this one can become V maximum. And enzyme activity increases with substrate concentration until maximum, where it becomes constant. So at Vmax, it has reached the saturation point and the rate of reaction becomes constant. And at half Vmax, if you have half Vmax, at half Vmax, we get what we call Michaelis Menten constant, which is regarded as Km. So Km is got by determining the half Vmax. So half Vmax, and you extrapolate on the graph, you get what we call the Km. So we are saying Km is equal to half maximum velocity of the enzyme. So that is what we, and Km is regarded as Michaelis Menten constant. Michaelis Menten constant, that is Km. And we are going to be using it in this discussion of ours. So this is how we can determine, this is the maximum velocity which determines the saturation point, whereby even though you continue increasing the enzyme the substrate concentration, the rate of enzyme velocity or activity remains constant. And we have seen that half Vmax gives us what we call Michaelis Menten constant. And this one we can also represent it in the form of Lineweaver-Burk plot, whereby under Lineweaver-Burk plot we have Lineweaver-Burk plot, Lineweaver, whereby this plot reports the reciprocal. Of these components, whereby we are going, if we had this, we are going to have 1 over V naught equaling to 1 over V max times Km. Km goes up because we are taking the reciprocal, then times 1 over substrate concentration, 1 over substrate concentration, this one also goes down, then Vmax goes down, then this one goes up. So we can even say it is equal to, we can present it in this version under Lineweaver-Burk plot, whereby we have Km over Vmax times 1 over substrate concentration, then plus, this one goes up, plus substrate concentration over 1. So this is according to Lineweaver-Burk, whereby he uses the reciprocal of this. So on representing this, this is a Lineweaver-Burk plot, whereby this is y-axis, this is x-axis, and here we have 1 over substrate concentration, here we have 1 over V naught, and whereby here we have positive side, and this is negative side, and here we have 0. So this side is negative, this side is positive. So if I am to plot this, it is going to give me a straight curve, and this is going to be 1 over negative 1 over Km. And this is the plot we can use this plot to determine the slope. So we can use it to determine the slope of the reaction during enzyme inhibition. So this is the one which is most accurate. The Lineweaver-Burk plot is most accurate compared to this plot. So in enzyme inhibition, we are going to use this Lineweaver-Burk plot. So this is known as Lineweaver-Burk. plot which actually determines the Km and the Vmax of enzyme activity in presence of inhibitors. So from this, after learning this enzyme kinetics, now we are going to look at enzyme inhibition. We're going to look at enzyme inhibitors. And enzyme inhibitors, they are categorized into two, whereby we have reversible and non-reversible and irreversible. Can you call it irreversible? So these are the two types of inhibition. And in our discussion today, we are going to dwell on the reversible inhibitors, whereby they are categorized into three, whereby we have competitive inhibition, we have non-competitive, then we have also uncompetitive inhibition. So these are the three types of reversible. Why do we call them reversible? These ones, during the inhibition, they form what we call non-covalent bond. They form non-covalent bond, so they can be reversed, or you can overcome the inhibition either by increasing the enzyme concentration or increasing substrate concentration. So we are going to start with competitive, we look at non-competitive, then we end with uncompetitive. And under competitive inhibition, in presence of competitive inhibitors, here the enzyme, the substrate plus and the inhibitor have same shape or configuration. They have the same shape or configuration, and because they are of the same configuration, they compete. These ones compete for the same binding, sites of the enzyme. And because they compete for the same binding site, we can easily overcome this reaction. This reaction can be overcome by increasing substrate concentration. When you increase substrate concentration, you can easily overcome this type of inhibition, which we are calling competitive inhibition. And in so doing, this one is going to cause the Km, Michaelis Menten constant, to increase, whereas the Vmax remains constant. So we shall have constant Vmax with increased Km. That is what we can talk about under competitive inhibition. And what can you capture? We are saying under competitive inhibition, if I can illustrate it here, the enzyme, if I have this as the enzyme, then this is the substrate. So the substrate and the inhibitor have the same configuration, so they compete for the same binding site. And in order to overcome this inhibition, I can increase the concentration of the substrate to overcome the inhibition, because they are all competing for the same binding site of the enzyme. And this one leads to increased Km, Michaelis Menten constant, and Vmax remains constant, as we are going to show it on the graph. So let us illustrate it graphically. So graphically using Lineweaver-Burk plots, we are going to see that if we have our plot here, and this is at 0, let's say this side it is positive, and here it is x-axis, then this is y-axis, and maybe this is our curve in absence. This is no inhibitor. Here it is in absence of inhibitor. We are getting our Km, 1 over K, negative 1 over Km. And remember here we have substrate concentration. Here we have, this is 1 over substrate concentration. 1 over substrate concentration. Here it is 1 over V naught. So after having this plot, in the presence of the inhibitor, we are going to see the plot shifting and the Km increasing. So the Km, the Vmax, here is the Vmax, remains constant for both. The Vmax remains constant, but the Km increases. It is increasing because we are moving from negative to positive side. So when you move this side, you are increasing. And when you move also this side, you are also here you are decreasing. But the good news is that they are all crossing the y-axis at the same point, meaning they have same Vmax. So Vmax is the same in the presence of competitive and with no inhibitor. So this is competitive inhibition, whereby we have seen Km increases, then Vmax remains constant. These are the things I want you to note under. Why? Because they have the same shape and configuration, competing for the same binding site, and I can overcome by increasing substrate concentration, which causes increase in Km, and the Vmax remains constant. So that is according to competitive inhibitor. This was number 1. So another type of reversible inhibition is non-competitive. Non-competitive inhibition. So if we have a non-competitive inhibitor, we are going to see, as the name suggests, non-competitive, meaning there is no competition. Here there is no competition. So we're going to see that the substrate and the inhibitor have different shape, or what you can call configuration. They have different configuration. And because they have different shape, they do not compete. They don't compete for the same binding site. For the same binding site, they do not compete for the same binding site. And because, so in illustration, if I have my enzyme here, this is the enzyme, then I have the substrate. This is the substrate. The inhibitor have different shape. And because they have different shape, they cannot compete for the same. There is no competition. So what happens, they can leave the substrate to bind. Then for it, instead of competing, it binds to the allosteric site. It comes and binds to other sites, what we are calling allosteric. So it binds to the allosteric site. And after binding to the allosteric site, even though you increase substrate concentration, the enzyme activity cannot be, the inhibition cannot be overcome, can't be overcome. So here you cannot overcome the inhibition by increasing substrate concentration. And because you cannot overcome this inhibition by increasing substrate concentration, Km remains constant. Km remains constant, whereas Vmax decreases. Vmax decreases. So you cannot attain max, since you cannot overcome this inhibition by increasing the substrate concentration, we are seeing Km remains constant, but Vmax reduces, meaning you cannot attain maximum enzyme activity. And this one we can illustrate on our Lineweaver-Burk plot. If we have this plot, this is y-axis, this is x-axis, positive side, negative side. And this is 1 over V naught, this is 1 over substrate concentration. And here, if this is in the presence of no inhibitor, here is no inhibitor. In the presence of a non-competitive inhibitor, we said Vmax decreases. Decrease means it is, because it is a reciprocal plot, you are going up. So the Vmax increases, whereas Km remains constant. So this was Vmax, 1 over Vmax, for with no inhibitor, which is high, but now it has decreased by going up. So this one becomes the Vmax, 1 over Vmax of the non-competitive inhibitor. So that's why we are saying for non-competitive inhibitor, we are seeing the Vmax decreases from this point to this point, because it is a reciprocal plot. So Vmax decreases, whereas Km is constant or remains the same. That's what we can appreciate, that negative 1 over Km has remained the same, both for with no competitor and also in the presence of a non-competitive inhibitor. So this is the plot for the non-competitive inhibitor. So we can end our discussion by looking at the last one, which is uncompetitive. Uncompetitive, and under uncompetitive, we are going to see, so this is the third type of reversible, which is uncompetitive inhibitor. So in the presence of uncompetitive inhibitor, what happens? The word is uncompetitive, meaning there is no single competition here in this type. So here we are going to see here the inhibitor. First of all, the substrate and the inhibitor have different shape. That is it. But still, the inhibitor, the uncompetitive inhibitor, does not bind to the enzyme, but only binds to an enzyme substrate complex. So the inhibitor binds to only enzyme substrate complex, not the enzyme. So what happens is, if I have the enzyme plus the substrate, this is the substrate, this is the enzyme, So they are going to first react to form enzyme substrate complex. So after forming enzyme substrate complex, that is when the inhibitor comes to bind. So in the presence of the inhibitor, because they have different shape, it comes and binds at the allosteric site, hence killing the release of the product. So here there is no release of the product, no product can be formed after it binding. So this is what we call uncompetitive. So it does not bind to the enzyme, but binds only to enzyme substrate complex, which is different from non-competitive. For non-competitive, they both bind to the enzyme. So the one which binds can form either enzyme substrate complex if the substrate has bound, or we can form enzyme inhibitor complex. But here we are getting the binding of the inhibitor and competitive after enzyme substrate binding to form enzyme substrate inhibitor complex. And because of that, we are going to see if we plot the Lineweaver-Burk graph. If we have a plot of Lineweaver-Burk graph, whereby here is 1 over substrate concentration, we have 1 over V naught, this one being positive side, this being negative side. So if this is my plot in the presence of no competitor, here is no inhibitor. No inhibitor, looks like that. So in the presence of uncompetitive, we are going to see both Vmax and Km decreases. So this one becomes the plot in the presence of uncompetitive. So this was negative 1 over Km, and this is the second negative 1 over Km. So we can appreciate that Km, as you're going more to the negative side, you're decreasing. So Km decreases. So we're going to end by saying that in this reaction, Km decreases. And also, since this was 1 over Vmax, and since this is a reciprocal, by going up, you're decreasing. So if it shifts from here to here, here 1 over Vmax also decreases. So it decreases. So we are saying Vmax decreases also. That is for any competitive inhibitor. And examples of competitive inhibitor we can have, like succinate dehydrogenase is an example of a competitive inhibitor. So in summary, we have seen for competitive inhibitor, because they have same shape, they compete for the same binding, and we can overcome by increasing substrate concentration. Km increases, that is Michaelis Menten constant, Vmax remains constant, so we can achieve maximum enzyme activity. Then we have seen under non-competitive, the substrate and the enzyme have different shape, and because they have different shape, they don't compete. So you cannot overcome this reaction. That's why Km remains constant and Vmax decreases. So these ones are also important to note under non-competitive. Then we have finished with uncompetitive, which binds only to enzyme substrate complex, and both Km and Vmax decreases. And that is what we can discuss for you under reversible competitive inhibitor. Thank you so much for learning with us at Medical Sciences. Please put the comment down in the section if you have enjoyed this video, and continue to subscribe. Thank you so much.